Alright everyone, welcome to another one of Mr. Martin's math videos. Today we're looking at chapter 6, section 1, Reciprocal, Quotient, and Pythagorean Identities from the BC Pre-Calculus 12 curriculum. And chapter 6 is devoted to the task of proving trigonometric identities. Developing proofs in math is one of the things that I love most about this subject. Math is one of the few subjects where the things you are taught have undeniable, irrefutable truths interlaced in every concept discussed in class. It is absolutely unfiltered truth. In many other subjects, it can sometimes be considered arrogance to say that you know something is true, but in mathematics we strive for the purest form of truth. This purity is preserved in what is known as a proof. All right, so an evidence or argument establishing or helping to establish the fact or truth of a statement. So we're going to be looking at proofs this chapter. Shout out to Mr. Greenlaw Math, who was behind a lot of the wording, or all the wording for this set of notes. To illustrate this point, let's demonstrate a well-known theorem many high school students should be familiar with, the Pythagorean theorem. Of course, we know this to be a squared plus b squared equals c squared. Well, kind of illustrated here on the right side. To many mathematicians, simply stating that a theorem is true is not enough. To be convinced that it is true, we require a proof. There are many different ways to prove the Pythagorean theorem. For example, there's 118 of them in the website that's included in these notes if you're ever interested. So what is a proof? What is the anatomy of a proof? There are many different styles of proving theorem, but in this course, we're going to be using a method called direct reasoning, which usually involves manipulating equations and using substitutions. All right, I like to think of the building of a proof in the same way that a carpenter builds a house. There are many tools required to build a house, such as a hammer, saw, drill, level, tape measure, etc. In math tools, the tools we are using are called theorems. Although this chapter, we use a special class of theorems called identities. These theorems serve as tools we use to prove unknown ideas in math. It's as if we use theorems to build more theorems, so things that have been proven in the past that are then used to help prove things in the future. The more theorems we prove in math, the more things we can do with math. Just like having more tools as a carpenter makes you better able to construct a house. All right. So this is a really fun chapter, though sometimes really challenging chapter as well. But again, part of the fun of this chapter is we're trying to figure out, okay, which tool am I going to use in which situation? And so you're going to be using different tools and different approaches, and the tools and approach that you use might not be exactly the same as the approach of one of your classmates, but you can still end up proving the same theorem that you've set out, both in a couple different ways. And so that's kind of the fun and creative part of this chapter. So let's start by taking a look at proving trigonometric identities. There are 3 types of identities you'll be learning about today. There are the reciprocal identities. There are the quotient identities, and the Pythagorean identities. So let's start with reciprocal and quotient identities. Guess what? You actually already know these. The reciprocal identities, when you're breaking down, are the cosecant, secant, and cotangent trig ratios, right? And we know that cosecant is 1 over sine theta, secant is 1 over cos theta, and cotangent, instead of being, is 1 over tan theta. All right. And we can also think of this one here as being equal, instead of sine over cos, it would be cos theta over sine theta. Okay, so these are some of the proofs that have already been, theorems that have already been established, and now we're going to use these to establish and prove other theorems. All right. Then there's also the quotient identities. I've already given you one in terms of cotangent theta, giving you cos theta over sine theta, and then the tangent theorem, quotient theorem, which is sine theta over cos theta, right? So we don't actually need to have this up here. We can put it down in this section here. All right, so these are some familiar things. None of these should be completely unknown to you at this stage of the course. So let's see how this works. So the first, we're going to verify a potential identity numerically and graphically. Okay, so this is the identity here that we're going to start with. Secant theta is equal to tan theta over sine theta. Here, this statement is saying that secant theta is equal to tan theta over sine theta. Is that true or false? How can we know that this statement is true? So we're going to run some tests to show that both sides of the equation are actually the same. All right, so test number one, we're going to substitute a value for theta. One of the questions here that you have to ask for these statements is, are there any non-permissible values to this? Okay, so for example, if you were to think non-permissible values, right, just when we're dealing with a rational expression, which, we have a rational component to this statement right here, we have to think about, is the denominator ever going to equal to 0? And that would give me a non-permissible value for theta. Okay, and so for example, for secant theta is equal to 1 over cos theta. So here, if cos theta is equal to 0, then my expression is undefined, right? And so where does cos theta on the unit circle equal to 0? Where does the x value equal to 0? And so we know that theta cannot equal pi over 2 and 3 pi over 2, right? Can't happen. Okay, because if I put, and I'm going to make sure my calculator here is in radian mode, if I put cos pi divided by 2 into here, I'm going to get 0, and that would give me undefined. Same thing with 3 pi over 2. All right. What about the other side? We said tan theta over sine theta. So here, where would sine theta be equal to 0? Right? Because if sine theta is equal to 0, if my denominator is equal to 0, then my whole equation is going to be equal to 0. Well, that is true for a radian of 0 and pi. All right, so just with these two kind of denominators here that we're checking non-permissible values for, I can determine that theta cannot equal 2 pi and any multiples of 2 pi when n, as long as n is an integer. Okay, so this would be my non-permissible value. All right, so this is something that you'll have to kind of, just like we've done in the past, non-permissible values, restrictions, these are things that at the beginning of the question you have to think about identifying before you move on. Okay, and some of the restrictions or non-permissible values will show up as you do the question as well, so be looking out for those. Okay, so let's substitute a value for theta. Let's do something simple here. So if I say secant 5 is equal to tan 5 over sine 5, right? I'm saying here that theta is equal to 5. I'm just substituting it. And if these are equal to each other, then both sides of the equation should equal the same thing. Okay, so in my calculator on one side, I don't have a secant kind of piece in my calculator. So on one side I'm going to do 1 divided by cos 5, and on the other side I can put tan 5 over sine 5 and see what that gives me. All right, so 1 divided by cos 5 gives me that number there. Okay, that's a lovely number. Let's try the other one. Tan 5 divided by sine 5. I press enter, and sure enough, they're the same number. Okay, so numerically, we have proved this to be true. All right, just by plugging in a number, we could plug in lots of other numbers. You can pause the video and plug in other numbers to make sure that I didn't just cherry pick 5 to double check for yourself. Okay, we can also graph these two sides of the equation and see if they're equal to each other. So in one side I have 1 divided by cos x. The other one I have tan, where's my x, divided by sine x. And I graph both sides. All right, and sure enough, I just get one line. Okay, now it's one line that follows the tan function, but it is just one line. Okay, the green line was the 1 over cos x, and the yellow line that I could see is the tan x over sine x. Okay, so you can see that they are the same line. So both graphically and numerically, we were able to show that this was this identity was true. This statement was true. Okay. Now this isn't really the best proof. What you want to do is prove it. What we're going to be looking at is proving it more in an algebraic sense, using theorems or identities that have already been proven. Okay, so let's see an example of that using algebra to simplify an expression. So again, first we have to start with our non-permissible values. All right, so some of the things you want to be looking at for your non-permissible values here is that cotangent, right, is cos x over sine x. So sine x can't equal 0. And then cosecant is 1 over sine x. And again, sine x can't equal 0. And cos because it's in the denominator, cannot equal 0 as well. So for my non-permissible value, and based on the previous question we looked at, when sine x can't equal 0 and cos x can't equal 0 as well, what we end up with is it's not theta in this case, it's at x, but x represents an angle nonetheless. X cannot equal to pi over 2 n and n e I, right? Any multiples of pi over 2, as long as the multiplier is an integer. Okay, if you're not sure how I got this, just go back in the video and see how we got this. Okay, because it's the same two denominators I'm looking at here, cos theta and sine theta, so I should get the same restriction. All right, so that's my non-permissible values here, way off on the side. Now let's see if I can simplify this. So one of the tricks that you want to use when you're approaching one of these statements that you're looking to simplify and using algebraic identities is you want to turn everything into cos and sine. Okay, you don't want to be using secant, cosecant, cotangent, tangent. As much as possible, change everything into cos and sine, and then start simplifying from there. All right, so that's what I'm going to do through substitution. I've already done a little bit when I was looking for my non-permissible values. So instead of cotangent, instead of writing cotangent, let me just rewrite my, that's the one I want, my for expression to begin with. So I had cotangent x over cosecant x times cos x. Okay. So in the place of cotangent, I'm going to substitute cos x over sine x, all right, and that's going to be over, and instead of cosecant, I'm going to put 1 over sine x, and cos x stays as is, okay? And you can see that this is cos x over 1 if you want to kind of visualize that. All right, so algebraically, next step, first I'm going to multiply the fractions in my denominator. So again, here I have in the numerator, I have cos x over sine x divided by, and this is 1 times cos x is going to be cos x over sine x. And sure enough, when you have cos x over sine x over cos x over sine x, when your numerator and denominator are the same, it's equal to 1. Okay, so I have simplified this expression using the identities or the toolkit that I have to change things up. And so this is kind of the approach that we're going to be looking at taking. Okay, so with this in mind, I want you guys to take a crack at this. Okay, first determine the non-permissible values for all of these, always in radians, and then of the following expressions, then simplify using algebraic means and the toolkit of identities that we identified here, reciprocal identities and quotient identities. So go ahead and pause the video and unpause when you're ready to go over together. All right, I hope that went well for you. So let's take a look at what we have here. Okay, so in this situation, it might be easier for me to simplify and then find the non-permissible values for each of these, just because when you simplify, that's when you end up seeing a lot of the numerators and denominators and so on and so forth kind of show up. Okay. All right, so here in this situation, secant, because I don't want secant and tan, I want to change everything into cosine and sine. I'm going to change secant into 1 over cos x, all right, and then tan into sine x over cos x. Okay, so here I have 2 of my denominators, right? Cos and cos in both situations here. Of course, if sine x equals 0, then your fraction is going to equal 0. Then you'll have a 0 in your denominator as well. So here at this stage, because both sine and cos cannot equal 0 in this expression, I know that, and this will be a common non-permissible value, this 2 pi n, where n is integers, a very common non-permissible value for I would say the majority of the questions you're going to face this chapter. Okay. Now for here, I'm gonna, instead of dividing fractions here, I'm gonna multiply by the reciprocal. Right. So I have 1 over cos x times cos x over sine x, and these cancel out. I end up with 1 over sine x, which is equal to cosecant x. Okay, so that would be my final simplification right there of the expression that was given to me. Okay, let's try this one. Okay, so here right off the bat, you can move pretty quickly here. However, because I have tan here, in this situation, it does give me non-permissible values. Of course, sine is in the denominator, and tan is in the denominator, and then the denominator of tan is cos, and so you end up with the same non-permissible values. Okay, and that's also when tan is equal to 0 around the unit circle, right, is when you have it's either equal to 0 or equal to non-permissible value at 0 degrees, 90 degrees, or I should say 0 radian, pi over 2 radian, pi radian, 3 pi over 2 radian, and 2 pi radian. So those are the multiples of 2 pi, and so it gives us our non-permissible values. So, and here right off the bat, algebraically, because I'm multiplying these up, these cancel out. I end up with, very quick, cos x over sine x, which is equal to cotangent x. And that's your final solution. Done. All right. Last one here. I'm going to change all of these into either cosine or sine. So this one I'm going to substitute 1 over sine x. And so it's just going directly below it is what I'm doing here. Okay. And then this is cotangent is cos x over sine x. And then secant is 1 over cos x. And then sine x is sine x. If you want, over 1. Easier to simplify things. Then you can cross things out, right? It's as satisfying as the rational problems we did in pre-calc 11. So cos x, sine x, sine x. What am I left with? 1, 1. I'm left with 1 over sine x. Okay. However, do note that in the denominator I had both sine x and cos x, which means my non-permissible values is that x cannot equal same non-permissible value as usual, 2 pi, pi over 2n, as long as n is an integer. Okay, here in both of these first ones, my mistake, I should have put x instead of theta. Okay, you're going to use a lot of x instead of theta in this chapter. So 1 over sine, that's not my final answer. I do want to change that 1 over sine x into cosecant x. All right. Good stuff. All right, so hopefully that went well. Let's look at another identity here. And sure enough, it's an identity that you also should kind of know already based on the unit circle here. Because I know that the equation of this circle is x squared. It is the unit circle. You can see 1, 1, negative 1, negative 1, right? 1 unit. X squared plus y squared is equal to 1, right? We've looked at this before in terms of using Pythagorean theorem, turning it to the unit circle equation. From here, I know that in the unit circle, I could substitute x with cosine and y with sine, right? So I can change the x into cosine, and here it would be squared x, because it's still x squared, so that would be the substitution for that. And then for the y, it would be sine squared x as well. Now, actually here I'm not going to use x because the variable x is already used. I'm going to use theta just to show that this is not the same x. Okay, it's the angle on the unit circle that would give me x and y coordinates of the point on the unit circle. Okay, so this is the Pythagorean identity here. All right, so just taking the familiar unit circle equation and converting it into a trig identity that we can use in some of these problems to prove some of these problems. So let's take a look at what we can do with this new tool in our toolkit. All right, so again, I want to approach this problem. I want to take on, change all of the trig identities I can to cos and sine. So this is going to give me cos squared x over sine squared x plus 1 is equal to 1 over sine squared x. Okay, the squared, nothing changes in terms of how these trig identities move with the squared. You just got to take the squared along with you. All right. Now here I have fractions in this rational expression. We know that if you're going to do a rational equation, we need to have a common denominator. So I'm going to work on this 1 here, and I'm going to change this into, so I can have common denominator across all 3 of these. So that's going to give me cos squared x over sine squared x plus sine squared x over sine squared x is equal to 1 over sine squared x. All right. Now, because all these are the same, you can cancel those out. And we can just by multiplying sine x on both sides, essentially what you do there. And what you end up here with is the Pythagorean identity. And because you were able to kind of show the Pythagorean identity here, you know that this side of the equation is equal to 1, right? So you have 1 is equal to 1 in the end is what you end up with. All right? So that would be your proof for this this equation here. Okay? Let's try another one here. Prove that 1 plus tan squared x is equal to secant squared x. All right, so again, same approach. Turn everything into sine and cosine. So 1 plus, and here I'll show my substitution in red, sine squared x over cos squared x equals 1 over cos squared x. Okay, and you kind of recognize where I'm going with this, right? I want that common denominator, so I'm going to substitute that one to cos squared x over cos squared x. Everything else stays the same, plus sine squared x over cos squared x equals 1 over cos squared x. Common denominator, can get rid of that. This cos squared x plus sine squared x I know is equal to 1, right? And so I get 1 is equal to 1. Okay? And I've shown, and I know that 1 plus 1 is equal to 1. That's just true, right? So I've proven that identity just like I proved it up here. All right? Let's do one more problem here. And this one is a bit of a challenge. It's a real brain tickler. Okay? So I want you guys to pause it and actually try this on your own. Remember the tools that you have, the reciprocal identities, the quotient identities, the Pythagorean identities. Try to use these, try different approaches. You have the whole page to kind of do trial and error with. Give it a shot. Give it the old college try and see if you can get it on your own. And then unpause the video and we'll do it together. All right, hopefully that went well, or at least you learned some things that don't work. Okay, so this is one way of solving it here. So I have one. I'm going to rewrite it so I can show more clearly the algebra that I'm doing to this problem. And I'm going to change everything to sine x, just it's easier to write than theta. So 1 over 1 plus sine x plus 1 minus 1 over 1 over 1 minus sine x is equal to 2 secant squared x. All right. So the first thing I can do for sure, and I'm actually going to do it right on this top line here, is I'm going to change this to cosine, right? So this gives me 2 over cosine squared x, okay? The 2 stays on the top. The cosine, it's 2 times 1 over cosine squared x, which is 2 over cosine squared x, all right? And now I'm going to try to figure out, I still want to look at those common denominators. That's a really good approach that we can get here. So here, by rationalizing, or by multiplying the denominator by its conjugate on the top and bottom, I can turn this into something that you'll recognize here. So 1 minus sine x on the top and bottom on this side, okay, by the conjugate. And then here, I'm going to do the same thing to this conjugate, but 1 plus sine x on the top and bottom. Okay, of course, these are in brackets, right? 1 plus sine x, all right? So this is going to give me the following. 1 times that is going to give me 1 minus sine x, okay? 1 minus sine x times 1 plus sine x is going to give me 1 minus sine squared x, which if you remember the Pythagorean identity, you should know that that is actually equal to cosine squared x, okay? Same thing over here. I get 1 plus sine x over 1 minus sine squared x, okay? Do the foiling if you're not sure about my math. Foil it out, okay? First outside, inside, last. And then 2 over cos squared x. All right. So now I have a common denominator. So here one thing I can do is, because these are common denominator, I can add the denominators, right? So the 1 plus 1 gives me 2. And negative sine x plus sine x cancel each other out, right? So I'm left with 2. And then, because of the Pythagorean identity, just rearranged algebraically, right? So this identity also, where is it? Where am I? Also exists as is. So if I were to minus sign on both sides here, I would have cos squared x is equal to, or theta, I guess I was writing up here, is equal to 1 minus sine squared theta, which is the situation I'm in the problem that we're solving right now. Okay? So these are both equal to cos squared x. And I mean, I can cancel things out, or I could just leave it as is here. But here, I've simplified it far enough that I've proven it. Okay, I don't have to simplify it anymore. It's clearly proven because there's the exact same symbols on both sides of my equation in the exact same order, in the exact same proportions. Okay, so that's how you do that one. So think about that kind of algebraic toolkit with your trigonometric identity toolkits. You want to combine those toolkits. So multiplying, rationalizing the denominator, multiplying by a conjugate, those kinds of things are also fair game in this chapter, which is what, for me, makes this chapter so much fun and why some students hate it. So this is your homework. The due date will be in the Teams for you guys. And if you have any questions, post your questions in the team channel as well. And hopefully this video